the title. Okay, you should better start recording at the very beginning. All right, so Dylan Butson will give his third lecture on vertex algebra from divisors in Calabi-Yau threefolds. Dylan, please.
Thanks very much, Jan. Happy to be here. As I've been saying, it's nice to get to talk so much about this topic because I've spent a lot of time thinking about it. So today we're going to give an overview of the correspondence, and I'm going to repeat a few of the things I've said in previous lectures in case anyone wasn't here for those, and just to remind you of the goal. So the goal of the lecture series and of today's talk, which will be kind of a summary of the main points, is to explain a correspondence between the enumerative geometry of coherent sheaves on, for now, just toric, Calabi-Yau threefolds, and the representation theory of various infinite dimensional algebras. And on the enumerative geometry side, to be a bit more specific, the invariants we're interested in are some invariants of coherent sheaves on surfaces in threefolds, which are called Vafa-Witten and Donaldson-Thomas, though, again, I probably won't explicitly use those words today. They're certainly there. And representation theory of various infinite dimensional algebras related to affine Lie algebras. There'll be vertex algebras, Hall algebras, and Yangians. And all of these will make an appearance today, and I'll explain a bit about how they're connected following various other people's work. And the methods, as I explained in the first lecture, will be kind of a classic paradigm in geometric representation theory that I like to call convolution algebras, which I'll recall again in the beginning of today's lecture, although I said it in the first lecture, but we were going a bit fast at the end because we were short on time, so I just wanted to kind of reiterate the points I made there. And yeah, so today we'll really go over everything. So I'll start with a brief review. Again, this is exactly the same slide that we had at the very end of the first lecture, or near the end. So convolution algebras are some associative algebras which are constructed geometrically by a kind of generalization of the convolution of integral kernels. And I thought maybe this time I could even just write what I was saying in words last time. So if you have some functions, f of x, y, and g of y, z, sort of functions of two variables, let's say on the same space, and then if you integrate over y, y and y, this will define some function, which we can call something like sort of f star g of x and z. And this kind of gives a 2-to-1 product on functions of two variables. And similarly, if you have a function just of one variable, then you can consider an integral like f of x, y, let me call it h of y. And this gives kind of an action on functions in one variable, so rho of f acting on h. This will now be a function of just one variable again. And so you can think of this as kind of a representation that takes f and acts on h and gives you a new function. So it takes a function of one variable and gives you a new function of one variable. And these kind of classical constructions that maybe you've seen in calculus or something, these are kind of the type of thing that's generalized by the formalism that I'm about to explain. So this should be the kind of basic example you have in mind. So, right, so there are also these natural representations. I was saying that, so you can construct algebras and you can construct representations. And the kind of more contemporary formalism for thinking about this in a more homological language is you consider a map F with X smooth and F proper, and you consider the self-fiber product of X with itself over Y, and the statement is that the appropriately shifted Borel-Moore homology groups of this space Z will be an algebra under a kind of construction like what I just wrote in the simple example of functions. And you can see this by considering the kind of, there's a map to from the triple fiber product to just the double fiber product, the self fiber product Z here. There are three different maps, pi12, pi23, and pi13. And you can first pull back along two of them, which were kind of like, and take this sort of product. That was the sort of writing the function f of x, y, g of y, z. And then you can push forward along the map that kind of integrates over the middle variable. And the result is a new function of the two variables. This is this kind of 2-to-1 product. And this is kind of a homological enrichment of that.
So you don't need the F to be proper, so the push forward, that makes sense in this case.
I did ask for F proper. Yeah, that's
Yes.
right. Yeah, exactly. Yeah. And similarly, if you have another space mapping to Y, you can form the fiber product with X. For example, W could just be equal to Y, and then you would just get the space X itself. That was kind of the example that I was doing before, and this will give you a representation of this algebra. And again, let me just say really concretely in some examples, if you just take n points mapping to a single point, then the algebra you get here is just the algebra of endomorphisms of C to the n, it's just GLN. And if you take W to be a point, then of course the fiber product of X and W over Y will just be X, which will just be n points. Its homology will be C to the n. And the representation of GLN on C to the n you find is the obvious one, just by matrices acting on vectors. And then more generally, if you have an interesting space mapping to a point, then you get the homology of X times X. And I mean, I was sort of ignoring the differential form degree when I was writing down those sort of calculus-based examples. But if you remember to keep track of the fact that they actually had to be differential forms, you could take some de Rham realization of this Borel-Moore homology group. For example, if you compute, so the definition of Borel-Moore homology is sort of upper shriek, lower star from the constant sheaf of a point. And if you choose a kind of model that in B-module language, you can write that in terms of differential forms, the relevant homology groups. And then you'll really find this kind of convolution of integral kernels that I was just explaining above. And then I mentioned this last time, but if you take the cotangent bundle of the flag variety mapping to the nil cone, then this is the kind of formalism that gives you what people call Springer theory, which is a way of constructing representations of things like the group algebra of the Weil group using geometric representation theory. And that's maybe one of the most famous classical examples in representation theory proper that uses this kind of technology. And our goal is to use this technology to construct representations of vertex algebras on vector spaces, which are kind of categorified enumerative invariants at the type of invariance that we were listing on the previous page. And it's in that sense that this provides the framework for the correspondence we're interested in today between enumerative geometry and representation theory. So another kind of repeat from the very end of the first lecture, but now I want to go through it a little bit more slowly, is the explanation of the kind of simplest example of the actual correspondence we're interested in, which was discovered by Gronowski and Nakajima independently. And the setting was the following. So let's let S be a smooth projective surface. And recall that we defined Hilbert of S in the previous lectures as the Hilbert scheme of n points on S. So this is a moduli space that parameterized the zero-dimensional subschemes of this algebraic surface S, where n denotes the dimension of the global sections of the structure sheaf of the given subscheme. Now there's a famous result of Koch, where I still didn't add the double O, which says that if you write down a generating function for the Betti numbers of the Hilbert scheme of a surface, there's a very nice closed form expression for this generating function, given just in terms of the Betti numbers of your original variety, which is perhaps surprising, and some, kind of complicated sort of combinatorial formula, which is very reminiscent of the type of formulas that show up when you compute the character of a vertex algebra, where the character is some kind of Hilbert or Poincaré polynomial of the sort of vacuum module of this vertex algebra. And indeed, what Gronowski and Nakajima discovered is that there's a natural kind of algebraic refinement of this formula that really tells you that these vertex algebras are showing up, kind of acting on the relevant vector spaces in the sense that I'm going to explain, using the technology of the previous slide. So let's let pi sub s sort of suggestively denote the direct sum of the homology groups of the Hilbert scheme. And this is the vector space whose kind of Poincaré polynomial is by definition, the left-hand side above here. And what Gronowski and Nakajima pointed out is that if you fix a subvariety of your surface S and you consider its fundamental class, so you take some class in the homology of your variety, then there's a natural correspondence between the Hilbert scheme of S and itself, where the number of points or the dimension of the structure sheaf of the subvariety, the zero-dimensional subschemes that these parameterize, is being changed by some, for now, let's say positive, for the sake of concreteness, integer k. So what is this correspondence? The underlying space is the space of pairs of subschemes such that one is contained in the other, and such that the quotient, it's easier to say this in terms of sheaves, but you could kind of think in terms of the structure sheaves if you like. The sort of quotient is, so it's going to be some other coherent sheaf supported on S, and we require that its support is contained in the subvariety C, which we fixed in the beginning. So for example, if you just took C to be all of S, you take the fundamental class of S here, which is a perfectly good choice of homology class. This is Borel-Moore, but I won't denote it throughout. So maybe even if S was not projective, although we've assumed it's projective so far, there's some fundamental class. In that case, this is really just, without any restriction, the space of kind of nested pairs of points in the Hilbert scheme. And what they showed is that if you pull back along one of these maps and push forward along the other, that induces a map between the Borel-Moore homology groups, which depends on the choice of fundamental class here. And if you sum these over all n, so if you kind of sum over all of the components in this direct sum that defined pi s, it gives you a map from, well, if you like, it takes as an input a class in the homology of S, and it induces an endomorphism of this module. So these endomorphisms showing up on the right-hand side here are like the endomorphisms that would be induced from representations of the type I explained in the previous slide. And as we'll see a little bit later, these are indeed endomorphisms sort of in the image of a geometric representation of the type that comes from convolution, like I was explaining previously. And we'll see that in a second. Anyway, so Gronowski and Nakajima, they built this map from the homology of S to endomorphisms of pi S. And what they prove, the kind of main theorem that you want to prove in this setting, is that this defines a representation of the algebra of modes of a vertex algebra, which I denote pi of S, where pi of S is the Heisenberg algebra, as I explained in the first lecture. This is kind of the most elementary example of a vertex algebra. And this to define such a vertex algebra, you need to take an abelian Lie algebra with a pairing, or a vector space with a pairing, and we'll take the homology of S itself together with the intersection pairing. And so this map defines a representation of the algebra of modes of this vertex algebra. And under such a representation, or sort of given such a map, we can then identify this vector space with some module. And it turns out to just be the vacuum module of this vertex algebra, the kind of canonical module that you'd expect. And in particular, I kind of mentioned that you might do this as an exercise last time when I stated this at the end of the first lecture, but this implies the above theorem by taking characters.
What's the role of C in this page? You fix some class C,
Right.
What's the role? Why you don't take like the whole S or something?
So you can, that's right, as I was mentioning. But if you think like in this Heisenberg algebra generated by the homology of S, there are a bunch of different kind of, there's sort of indices for all of the different homology classes, and you want to know how all of them act. So this is sort of a stronger
I don't get the formula does not involve C on the left-hand side and on the right-hand side. So why should I care?
The point is that on the right-hand side, you see all of the Betti numbers of S appearing.
Yes.
So there's some kind of sum or product over different homology classes. And that's what C is. C is just a choice of homology class.
Well, frankly speaking, I do not see it. I do not see the point.
Yeah, let me say again. So I was answering, because you asked to refer back to this formula, I was kind of answering in a direct way about that. But again, let me emphasize, like, to define a representation of this vertex algebra, if you just wanted to define a representation of the plain one-dimensional Heisenberg algebra, like the enveloping algebra of GL1 hat, there's kind of only a single series of generators, BK, that you need to define, because the Heisenberg algebra is generated by some, integers many generators, BK. Mm-hmm. In this case, we have a Heisenberg algebra built out of a higher dimensional vector space, namely the homology of S. And in order to specify a representation of this bigger algebra, which looks like a tensor product of dimension of the homology many Heisenberg algebras, I mean, at least in terms of size, again, really, the relations are determined by the intersection pairing. That's the statement of the theorem. in order to define a representation of this larger algebra, we need to say not only a bk, an endomorphism bk for every integer k, we need to give an endomorphism bkc for every integer k and every element c in the homology.
And that's what the C, class C is used in defining this alpha k. Actually, alpha k depends on the C.
Exactly.
Homology class. So when you define the Heisenberg algebra, you also need the invariant bilinear form. Is the invariant bilinear form just a Poincare duality form?
That's right.
Okay.
The intersection pairing on the homology. Yeah, that's right.
Yeah, thank you.
Is that cool, Jan?
Yeah. This is fine. I mean, my concern is that the Gödge theorem, it does not involve C, but you say that when you want to define the action of the Heisenberg generators, so but it's kind of, I'm still a bit confused. If your C is the whole surface S, this correspondence is just adding, like in the simplest case, k equal 1, whatever, just adding a point to the Hilbert scheme. So what's the geometric interpretation if I realize my homology class by a cycle? What's
right.
yeah.
So it's adding an extra restriction where you consider adding points which must be contained in that cycle.
Okay, great. Yeah, that's what I expect. Okay, good.
So yeah. Great. I kind of said that in words, but yeah, I didn't write it on the slide.
Okay.
Cool. So this is the kind of
if the notation alpha k is just written as a C sub k, so that would be perfect for Heisenberg vertex algebra generators.
yeah. There was some kind of funny notational choices to make.
I understand that. Thank you.
No worries. So, right. So I was just saying this is kind of the model example for the kind of thing we want to do. We want to have some kind of moduli space of coherent sheaves on a surface. And then we would like to build an action of the algebra of modes of a vertex algebra on the homology of this moduli space of sheaves. And so we're going to sort of aim to do that. Right. So I decided I should include a quick kind of explanation, and I thought it would be a good opportunity to introduce this sort of equivariance that's going to play an important role today. That's the reason why, for now, we need to restrict to toric threefolds. So I wanted to explain a proof, a sort of a sketch of the proof of this Gronowski-Nakajima statement in the case where your surface was C2. Now, of course, C2 is not projective. And as a result, a certain map that we'll use in the correspondence will not be proper. And so naively, the previous construction doesn't work. However, C2 does have proper fixed points under the action of the torus C star squared, which acts on C2 in the obvious way by weight, 1, 1 on the two factors of C. And let F denote the field of fractions of the equivariant cohomology of a point with respect to this torus, which will just be the field of rational functions in two variables, which I'll call epsilon1 and epsilon2.
So in 2 dimensions, you do not need the Calabi-Yau action of the torus, yeah?
Yeah, that's right. Exactly. It's just a sort of full torus, which later in 3D we'll see is kind of identified with the Calabi-Yau subtorus. So in this setting, we're able to use the localization theorem for equivariant homology or cohomology in order to give a very nice explicit combinatorial description of the vector space and see that it really looks like the Fock module we wanted it to be. So the statement is that in for each n, if we look at the fixed points of Hilbert C2 under this torus action, which naturally kind of acts on Hilbert because it acts on the underlying variety, the fixed points in Hilbert will be identified with the set of partitions of length n.
What's a letter? How to read it? It's
I used it in the paper because I ran out of letters. It's a Hebrew letter, and it's supposed to be kind of like a Hebrew P for points. Or it also, yeah, it's kind of like F as well. It was a nice choice of letter for fixed points, but somehow, for example, you see F is appearing above here. P was already taken, and anyway. So this is denoting the set of partitions of length n, and what I've written here is the correspondence. So if I have a point in the Hilbert scheme, which, as we've explained, it's parametrizing the ideal sheaves, being a fixed point, first of all, you should note it's going to restrict the possible support of your sub-scheme to just be at the origin, at the single fixed point of C2. Certainly any subvariety which is not supported there, or any sub-scheme which is not supported there, will not be invariant. But if you take, for example, this ideal, which is indeed supported at the origin and invariant under T, you can see that it corresponds, if you think about the kind of co-kernel in C adjoin xy of this ideal, you can kind of draw it pictorially, and it clearly forms a partition. If you just ignore the little labels in these boxes and think about this sort of Young diagram as being just a partition, this is the correspondence.
Nice day. Take care. See you later, 40. 314.
Pardon me?
314.
Well, I think maybe someone doesn't know that they're not on mute. So anyway, I just wanted to point out one other thing, which is that we can also parameterize this set by assigning to the partition a formal variable for each, for example, column in the conventions I've chosen here, and taking a power of that formal variable given by the number of boxes in that column. So this partition I've drawn here would correspond to Z1 cubed, Z2 squared, Z3, Z4. And under this identification, this module that we're interested in, the direct sum of, I've now localized, but never mind, the localized equivariant homology groups of Hilbert C2. By the localization theorem, this will be a direct sum over fixed points of the homology groups just of points. And then under this final identification, this will just look like a polynomial algebra over this base field, the field of fractions of the equivariant homology of a point, in infinitely many variables.
So why do you need homology here when you localize? It's more with respect to the T action, it's more natural to use cohomology.
I think that I would say so they'll be identified in this setting, but because the general non-equivariant statement uses homology, to my eye, I think it's more natural to call it the homology. For example,
because I even do not know, I mean, this, when you speak, for example, you will do some computations, yeah, probably, and for cohomology, there are some textbook localization theorem. For homology, I mean, it's not
for homology,
but still, when you see the problem when you work in non-equivariant settings, so your homology, in fact, as you said, it's Borel-Moore homology, so it's just dual to compactly supported cohomology. This is it. That's essentially that's the definition.
And here I also mean equivariant Borel-Moore homology, which again is always upper shriek lower star.
Okay. All
And
right.
it is defined. And I would, for the localization result, there's this very nice paper of Goretzky, Kotwitz, McPherson on Kazul duality and equivariant cohomology. It's really fantastic paper. And there they prove a localization theorem with more general coefficients. They even prove
Yeah,
sort of
okay.
a stronger form of the localization theorem. But in particular, if you're willing to use coefficients in the dualizing sheaf, which you certainly can by their results, then you have localization for a Borel-Moore homology.
Okay, good.
Right, so let me continue. So the conclusion here was that we can directly calculate the underlying vector space and identify it with a one-dimensional, the sort of Fock module over a one-dimensional Heisenberg algebra, but over this base field F, which was the localized equivariant cohomology of a point with respect to C star squared. That's what I just wrote here. Great. And now the theorem, the analog of the theorem in this case, will be that you get a representation of a one-dimensional Heisenberg algebra, but it will be over this base field. And in fact, the level of the Heisenberg algebra will depend on sort of the specialization you might want to take in the base field. And the way that the level will depend is by -1 over epsilon 1, epsilon 2. And the way that this shows up is as kind of the equivariant volume of C2, or the pairing between the fundamental class of C2 and itself under the equivariant intersection pairing. And in particular, you can see that if you try to turn off the equivariant parameters to set like epsilon 1 and epsilon 2 to 0, then the non-compactness is kind of causing a sort of divergence here. You're getting an infinity. And that's kind of a clue that you really needed to do this localization.
So this is typically a kind of four-dimensional phenomenon. So when you go to 3 Calabi-Yau, you will not have this problem. Because this factor, it appears in this counting of instantons story. I know this Nekrasov, and later some mathematical paper by Nakajima Yoshioka. Yeah? So it's kind of factor which appears in the asymptotics, which gives you the prepotential, but it's four-dimensional. Yeah. So which means in three-dimensional Calabi-Yau, you will not have this, I think.
Well, I mean, there will be some analog of it, but there's something a bit more subtle that can happen where you should think of the C2 that we're describing here, as we'll see later, it should be thought of as embedded inside of a toric C3 as one of the coordinate hyperplanes. And then depending on which of the coordinate hyperplanes you chose, you would get a kind of different dependence on the equivariant parameters. Yeah,
but it's kind of, well, I am sort of maybe ahead of what you want to say. But you see the way we approach that problem in C3, we essentially like follow similarly to Schiffmann and Vasserot. We considered it as three problems for three coordinate planes. So then we reduced everything to two-dimensional partitions. But I'm not sure that this is conceptually a good way to define it. Kind of. Maybe from your perspective, when you have a divisor which is toric invariant, maybe it's natural. But if, for example, your divisor is not toric, and so then.
Yeah, so I do believe that if you were not toric, but instead you had some sufficient properness assumptions, that it's possible you could do the more general construction beyond the toric case. But at some point, you need to deal with this lack of properness. It's not a problem for constructing the action of the positive modes, but it will be a problem for constructing the action of the negative modes. It's always there. So
yeah,
either...
what I mean that even in this Goethe formula, which was on the previous, you can use torus localization to prove it, as you are explaining now. But there is, of course, an analog, and I think Goethe himself proved it for arbitrary surface. Yeah. And then you do not have the torus localization. Instead, you use sort of perverse sheaves on the moduli space on Hilbert scheme instead of torus localization. And in this case, this divergence is not visible. That's what I mean. And if you, for example, had a similar story with 3 Calabi-Yau non-toric, then you can hope, probably, that there is still this main result, which you will explain us, but with a different approach, which does not use localization to different torus invariant components of your divisor, I would say.
Yeah, I have a similar expectation. I was sort of just saying that I still think you'll need some properness to do something like that.
Yes.
But as long as you have that, then I totally agree. And yeah, optimistically, the goal of this sort of program is definitely to go beyond the toric case. You know, I think that algebraic geometers already know a lot about the geometry of toric varieties, and maybe it will be hard to teach them something that they really didn't know. But hopefully this philosophy, I think the expectation is it can go beyond the toric case, and maybe it will produce useful invariants or like useful algebraic structures on invariants in the non-toric case indeed.
Okay.
So let's proceed. Right, so this defines representation of the level k equals minus 1 over epsilon 1 epsilon 2 Heisenberg algebra, as I said. And I just wanted to remark that there's a kind of slick way of calculating this, again, using localization results, which is, it's not hard to check that you can identify the endomorphisms that come from, for example, the fundamental class of C2, which is a generator for the equivariant homology of C2. You can identify them with the following kind of concrete expression in terms of some polynomials and equivariant parameters. And using this expression, it's kind of a fun exercise to check in, like, say, by hand for the low values of n, the sum n's here that correspond to low values of n. You can kind of check by hand that that you have this commutation relation, that the modes b minus 1 and b plus 1 commute to give you the identity times this 1 over epsilon 1 epsilon 2 factor. And again, this factor will show up as the sort of equivariant volume of C2, or the kind of equivariant Euler class of the tangent space at the origin.
Yeah, I'm a bit confused again, because you insisted on this homology class C inside of your surface. So here probably you are looking for equivariant homology. So there are not too many possibilities. That's what I mean.
So here it's just one dimensional over the base field, the same way that, you know, the homology of C2 is just trivial. Yeah. But the Borel-Moore homology of affine space is, you know, concentrated in a single degree, and it's generated by the fundamental class. So that's the class I chose.
It's a little bit misleading. There are no other things except of C square.
Yeah, in this example, that's right.
What is the epsilon t of the?
So this is the equivariant Euler class of this
Okay.
bundle, which in this case,
Oh.
I mean, it's a tangent space at a point, so it's just a vector space.
Okay.
And you can calculate it. It's just the product of the characters that show up. If you look at, so because this is a fixed point, the torus acts on the tangent space there. And it's just the characters of the torus that show up. You just take the product of them. So for example, if you took the origin inside of C2, that you would find epsilon1 times epsilon2 as this equivariant Euler class. I didn't want to dwell too long on this computation. The main thing I wanted to introduce was the role of the equivariance in curing this non-properness, and the fact that the kind of level that shows up here is going to depend in an interesting way on the equivariant parameters, which is going to be a kind of important phenomena that will play a role today, and especially in the final lecture tomorrow, when I talk about the more general vertex algebras. These kind of dependences will be crucial to encode the geometry of the toric threefolds in these vertex algebras. Okay. So now I want to talk about the first and kind of maybe most important step in generalizing the construction that I was discussing previously, which is we'll keep the underlying surface to just be C2. We won't graduate to threefolds yet even, but I'll want to describe sheaves of higher rank. So recall that the Hilbert scheme of C2, we described it as a certain moduli space of torsion-free sheaves of rank 1, and equivalently as representations of framing dimension 1 of the ADHM quiver. And there's a very natural question, which is what happens if we consider instead higher rank torsion-free sheaves on C2, framed at infinity, or equivalently higher framing dimension representations of the ADHM quiver. And an answer was kind of conjectured in physics by Aldai, Gayoto, and Tachikawa, and I'll state the kind of conjecture, and it's now a theorem by the authors that are listed here in a minute. But first, I just want to make the following sort of key observation, which is if we define the analogous vector space on which we would hope to define a representation of some vertex algebra, namely the direct sum of the localized equivariant Brellmore homology groups. I'll probably stop saying all those adjectives and just say homology in future. So these homology groups of the moduli spaces of torsion-free sheaves of rank R and second Chern class N, summed over the choice of second Chern class, as in the rank 1 case, then by using equivariant localization with respect to an auxiliary action of the maximal torus of GLR, which acts by changing the framing. Again, I don't want to dwell too much on the details, but by using, again, equivariant localization, one can see that this is identified with a direct sum of tensor products of the homology groups from the rank 1 case. And in fact, in total, just by some kind of simple algebraic juggling, we can actually see that this is identified with a tensor product of R copies of the same vector space we had in the C2 case, which was just the vacuum module of the one-dimensional Heisenberg algebra. And again, everything throughout the rest of the talk will be over this base field, the localized equivariant cohomology of a point, but I'll omit the kind of tensor over F from the notation throughout.
I forgot your notation. Your P of C square, did it depend on N?
It was the direct sum over all n's. It
Then
was
probably
this.
you should take the direct sum over all N in the previous isomorphism. Here is fine, but here in the middle, yeah.
Here, yeah, sorry. I didn't want to, I wanted to fit it on this line, but indeed you're summing over N1 through NR that sum to N, and you're summing over this total sum N. That's right. Yeah, so there's kind of like also a plus over N here, but it wouldn't fit, or this would drop to the next line, so couldn't put it. Indeed. So at the level of vector spaces, we see that we just have a tensor product of r copies of the rank 1 guy. So that's fairly simple. And indeed, Baranovsky proved that using a similar argument to Gronowski-Nakajima, you can get an action of a kind of higher dimensional Heisenberg algebra, a tensor product of our Heisenberg algebras, which I think is not such a surprising statement. Probably the original authors also could have proved that if they wanted to. But there was a more impressive conjecture, which was now a theorem due to Schiffmann-Vasserot, Maliko-Kunkov, and Braverman-Finkelberg-Nakajima separately, although the last one was not completely independent and also extended the result to ADE instead of just type A, but never mind. But the statement of the AGT conjecture, I'll call it, is that the relevant algebra that actually acts here is the algebra of modes of a much more interesting vertex algebra, which is called the principal affine W-algebra of GLR. And it also has a level parameter. And it turns out that the level of the action is up to a shift by minus the dual Coxeter number given by the ratio of the two equivariant parameters.
Why they are not symmetric? You cannot interchange epsilon2 and epsilon1 in this formula.
So in fact, right, so that's a great question. And in fact, so if you consider the shifted level, kappa plus h check, then you see that swapping epsilon1 and epsilon2 sends kappa to the kind of Langland's dual level, kappa star. And there's a theorem of Fagan and Frenkel that if you exchange kappa and kappa star, and you exchange your Lie algebra with its Langland's dual Lie algebra, there's an isomorphism of the two W algebras. In this case, because we have a GLR, it's self-Langland's dual. It's simply laced and you've included the Cartan, so nothing is happening under Langland's duality. So it is in fact true that the algebra that's acting is isomorphic if you interchange epsilon1 and epsilon2, but that's actually kind of a deep fact. And it's kind of, if you like, it's kind of a cool feature of this geometric construction that this relatively deep fact about what is related to the geometric Langland's correspondence is appearing almost trivially from the symmetry of just exchanging the two coordinate axes. Okay. So yeah, that's
this is possible because the GLR has a one-dimensional center, so which in the affine vertex algebra you will have a copy of a Heisenberg, and for the Heisenberg basically the level, and you can always change.
It's not like that.
It's not like that.
The Heisenberg are just the same for all non-zero levels. They're just canonically identified. Yeah. This is only two special levels.
I see.
Any other level, it just won't be the same. It's really a kind of important, deep thing. It's not just some trivial reparameterization. The fact that you have GLR instead of SLR, I was commenting, if you had SLR, then the dual algebra would be for PSLR at the opposite level. And the fact that you don't see two different Lie algebras showing up here is because you kind of left your GL1 inside.
And here when you try to make epsilon, one of the epsilons equal to 0, you will get a kind of nice quasi-classical limit because it has a big Poisson center on the critical level.
That's right.
Yeah, so it corresponds to this. The fact that the algebra of differential operators on the power of the determinant bundle on band G with this minus h bar is commutative. So then
exactly.
That's what Frenkel and Hagen and Frenkel proved long before Bill. Well, before Bielenson and Drinfeld, this story. but it was
Absolutely.
a motivation. Okay.
And indeed, even the more general statement about the general level Fagan-Frenkel duality was due to Fagan and Frenkel. Absolutely not Billington and Drinfeld. It predated them. But I think in retrospect, it should be understood as a kind of aspect of the geometric language program, even though it sort of maybe predated their book. Okay. So the proof. Unfortunately, the pause feature doesn't work for these kinds of figures, so I had to show you all at once, but let me say a few words about how a theorem like this is proved. And sort of all the features are going to kind of inform our generalization going forward. So I know there's a lot of things on the page, but bear with me. So let's start here. So this question, question, question arrow is the map that we're trying to construct. We would like to prove that there exists a map called question, question, question from the algebra of modes of this W algebra to the endomorphisms of this vector space. And since this vector space is a tensor product of R copies of the Fock module, we can, of course, write its endomorphisms as a tensor product of the endomorphisms of the individual tensor factors. And we know from the rank 1 case that we do have a representation of a tensor product of R copies of the Heisenberg algebra on this tensor product of R copies of the module. So this guy down here we have. And the result of Fagan-Frenkel, which actually allowed them to deduce the duality that I was mentioning before, is in fact that the algebra of modes of the W algebra embeds into this tensor product of the algebra of modes of pi k. So maybe I wrote that here. Let me see. Yes. So, well, maybe I don't want to include that just yet. Let me go back. So there's this embedding. So this is known. So we already kind of have a candidate. We do know, just at the level of pure algebra, we know that this algebra includes into a tensor product of Heisenberg algebras, which does act on our desired module. However, there's no guarantee that this action is the one that we're constructing geometrically. That has not been promised to us yet. And so it remains to somehow deduce that the geometric action we're getting coincides with this action. And in order to do that, the key realization is that there's actually an auxiliary algebra, which is also acting in this setting, which is called the Yangian of GL1 hat, or the affine Yangian. And you can prove, independent of this description of the W algebra, that the affine Yangian of GL1 does act, so there is an arrow like this. It does act on the relevant vector spaces. So we do have a representation of this guy. And moreover, there's a natural coproduct on this algebra, which decomposes, well, which identifies, so because it has a coproduct, we can take tensor products of representations. And this coproduct identifies the tensor product representation of R copies of the rank 1 guy with the same vector space, but the kind of representation just on it geometrically. So we have kind of commutativity of this outside square using this coproduct map. And moreover, the rank 1 representations are known to factor through the enveloping algebras of Heisenberg algebras. So we have the commutativity of this outside square. And we know that, in fact, the bottom map is indeed factoring as indicated. So now, what we would like to show is that we can identify the essentially, let me say it like this. We would like to show that this action of GL1 hat on this tensor product module actually factors through this W algebra. So if we could show that, if it's acting here, and if it factors through a quotient, which can be identified with this W algebra, that would in particular imply that we have the kind of desired map. So far, that's kind of tautological, but the point is that we have a lot of this extra structure here. And now to say a little bit more about what the image of this W algebra inside of this tensor product of Heisenberg algebras is, let me recall the precise statement of Fegan-Frenkel, which is that the image of this embedding of vertex algebras can be characterized as the intersection of kernels of certain maps, which are called screening operators. And they're not appearing here. But the key point is that there's a very precise kind of algebraic constraint that you can write down, which describes the image of this embedding. And so we would somehow like to compare that with the image of the Yangian representation that's appearing here. And so what one can do, somehow or other, to my eye, more or less by brute force, it was calculated, for example, by Schiffmann-Vasserot, that if you look at the image of the Yangian of GL1 hat inside of here, by taking the coproduct and then applying this kind of tensor product projection map, that this image is actually the same as the desired intersection of the kernels of screening operators. And that actually implies that this action, which is kind of going all the way around the bottom here, does factor through a quotient, which is the W algebra. And it in particular implies that the kind of geometric action here, the kind of question mark map, does come from the W algebra. So this is the basic outline of the proof. Of course, this is a hard theorem. This is it was all of the proofs of this occupy papers that are at least 100 pages and published in good journals and all that. So I can't explain everything here, but this is kind of the basic idea. And I wanted to outline it in this way to say that our goal, which has not, personally, I haven't kind of completed the program yet, but the idea is that we should generalize all of the ingredients in this proof. So this is right at the bottom. Sorry, Jan, if you can't see it. So we're going to generalize these Yangians that show up here, the Yangians of GL1 hat.
Oh, I see it.
Excellent. We're going to generalize these kind of interesting vertex algebras, these W algebras. They'll have some kind of free field realizations in some easier vertex algebras analogous to these Heisenberg algebras, the pies. So there'll be some kind of embedding iota Fegan-Frenkel, some generalization of that. And we'll have some kind of course, representations on these vector spaces related to enumerative geometry, and some kind of quotient maps from these Yangian-type quantum groups that we want to construct to our various vertex algebras of interest. And we want to use a similar proof strategy as this kind of outline of Schiffmann-Vasserot in order to produce the kind of general statement. And to tell you sort of ahead of time, I have not given a kind of complete proof of this statement, or with collaborators, nor by myself. But most of the ingredients are defined, and there are a lot of very convincing checks that everything is working. And perhaps the biggest obstacle, which I can't generalize, is the existence of this coproduct, which is somehow compatible with these free field realizations. And there are some cases when the coproduct is known by pure algebra methods, which are very computational and kind of technically difficult. But they aren't known at the generality that we need them. And even if they were known using kind of similar methods to the sort of status quo in that field, the kind of combinatorial difficulty of the definitions, I don't think would allow for a proof of the main conjecture. I think that a more geometric construction of the analogs of these coproducts is really what's missing to kind of complete this program. That's sort of a preview for later. But more or less everything else, I claim I'll explain, has a kind of natural generalization, and a lot of the sort of partial results have been proven towards kind of generalizing this theorem to divisors and toric Calabi-Yau threefolds. So that's what we're going to kind of discuss.
Can I ask a quick question before we turn to the next page?
Of
so
course.
the Ficken-Frankel embedding, is that only for the universal enveloping algebra, or is that actually for the vertex algebra? The W-algebra embeds into the tensor products or copies of the Heisenberg.
Yeah, so it's actually for the vertex algebra. And
Okay.
here, yeah, it induces something at the level of algebra of modes, and I was being a bit sloppy about distinguishing.
Oh,
but
that's
yeah,
fine. That's fine. I just want to know. Thank you.
Yeah, that's right. It's an embedding really at the level of the underlying vector spaces.
Mm-hmm.
Let me just grab my phone because I realized I haven't been keeping track of the time. I know you said that I could go long today, but I don't want to go too late. Whoa.
No, that's fine. You are not
Already.
I mean, your own restrictions is the only.
No, I don't, especially if I mean, at some point I'll need to eat dinner, but I'll be okay for now. All right, so let's press on. So towards generalizing the Yangians that show up here, first, I kind of took as a black box here that there actually were these Yangians that also acted. And I want to explain a little bit about the geometric origin of the Yangians, even in this simple kind of C2 case, before proceeding to talk about kind of the generalization of the whole story. So where do these Yangian actions come from geometrically? And the answer is the theory of cohomological Hall algebras. So recall that in the previous lectures, we described this stack, which I call M sub n of C2, of compactly supported coherent sheaves on C2, whose space of sections is of dimension m. And we identified it with the stack of representations of a quiver with relations given here. So it's a single vertex, two loops, and a relation that the two endomorphisms commute. Now, using similar methods to what I explained on the very first page, if one takes the direct sum of the homology groups of these stacks of quiver representations, they form an algebra under some natural correspondences, where the correspondence is the space of short exact sequences of quiver representations, which has three maps to the space of quiver representations, namely taking the sub-object, the quotient object, or the full object in the short exact sequence. So one naturally obtains an algebra in the way I was explaining before, and this is called the pre-projective cohomological Hall algebra. And it was studied probably by many people, but Schiffmann-Vasserot studied it, and especially in this case, quite a lot. And Yaping Yang and Gufeng Zhao have a paper also, which studies kind of maybe in a little bit more general terms, the pre-projective coha. And now, again, similarly to what I explained in the outline on the first slide, there are some natural geometric representations of these pre-projective cohomological Hall algebras that come from studying framed representations of this quiver. And there's a very nice paper of Yang that explains this general principle. So if you had kind of, the framed version of this quiver, which I'll recall sort of add a framing node like this, then there's a correspondence that modifies a framed representation and takes it to another framed representation by kind of extending the vector space here. So formally, you can write the moduli space of short exact sequences of framed representations where the sub-object is of framing dimension 0, And so the quotient object is of the same framing dimension, but the actual dimension vector at the principal node will be modified. And considering, a similar push-pull argument, like I outlined on the first slide, gives rise to sort of natural geometric representations of these pre-projective cohas on these vector spaces, which are the direct sum of the homology groups of the framed representations, where we sum over the dimension vector, but we fix the framing vector once and for all. So this gives a representation of some algebra here on our vector space of interest. And it turns out that if you look inside of this pre-projective coha, if you look at the first summand, it's the moduli space of compactly supported coherent sheaves whose space of sections is one-dimensional. So those are just structure sheaves of points. And so the moduli space of such is actually just a copy of C2. And so we have a copy of the homology of C2 sitting inside of this pre-projective coha. And this representation, if we restrict it to this subspace, the homology of C2, precisely coincides with the map that we discussed earlier that we constructed out of correspondences. And that kind of gives a flavor for where those correspondences came from. They were really kind of correspondences that could have mapped to three spaces, and then we sort of picked a class in one of the spaces in order to induce a correspondence just between the other two to get an endomorphism as opposed to a representation. Sort of where those Gronowski-Nakajima correspondences come from. And so that defined the alpha minus 1. And more generally, if we look at the image of this entire Hall algebra, which it's by now actually been proven that this is spherically generated, so I could equivalently have said the spherical subalgebra here. But if we look at the image of this under the representation, we'll find that it fills out all of the so-called positive modes, or the positive half of this algebra of modes of the Heisenberg algebra, which is the subalgebra generated by the BKs for all of the negative Ks. And the heuristic here is those are the generators in the Heisenberg algebra that act by kind of raising operators, or kind of they generate your Fock module out of the vacuum. But this cohomological Hall algebra action by itself doesn't generate the lowering operators, those endomorphisms of the Fock module, which correspond to BK for K positive, which kind of decrease and bring you closer back down to the vacuum. The things that we identified with kind of the derivatives with respect to those formal variables in the description of the Fock module we gave. However,
is it just a notational overlap of the two Ks, the high K? I thought K is the level.
Yeah, sorry about that.
The other one is the other K is just the modes. That's a different one.
Yeah, that's great. So let me call this, thank you. Let me call this BL for L less than or equal to 1. Yeah, thank you very much. Yeah. Okay, great. And so I was saying, although this algebra here, this so-called pre-projective coha, doesn't see the full algebra of modes, it kind of only builds the positive half. There's a natural algebra which kind of extends this, and it's precisely this affine Yangian of GL1 that I was mentioning in the previous slide. So the affine Yangian of GL1, I'm not going to give the kind of generators and relations description, but it has a triangular decomposition as a tensor product of three factors, the middle of which is a commutative subalgebra. Doesn't commute, it's not central, but it's commutative itself. And both the positive and negative halves of this triangular decomposition are isomorphic to this Hall algebra and its opposite, respectively. And again, the standard statement here, you should say spherical, but I think in the equivariant case, it has been recently proved that this is actually spherically generated. If I understand correctly, I think there is some recent work of Ben Davison on this particular example that showed that. So as a result, well, it's not too hard to see that by taking adjoints, you can extend this representation of the Hall algebra to its opposite algebra. And then, you know, being a little bit careful about some of these central generators, or pardon me, this kind of commutative subalgebra, the generators in there, it's possible to see that actually, first of all, that this extends to a representation of the Yangian of GL1 hat, and moreover, that this representation, it does factor through the algebra of modes of the full Heisenberg algebra. So this is the kind of natural geometric origin of this action of the affine Yangian as a kind of double of the pre-projective cohomological Hall algebra. And this is the way that it shows up, for example, in Schiffmann-Vasserot. And now, now that we've sort of seen where the Yangians come from in this story, the Yangian of GL1 hat, towards moving to the generalization to toric threefolds, I want to point out that for a quiver with potential, rather than a Nakajima quiver variety, as we were studying above, if you have a quiver with potential, there's a similar construction of the so-called critical cohomological Hall algebra, or Calabi-Yau cohomological Hall algebra, which is an algebra whose underlying vector space is the direct sum of the, again, I use equivariance here, but the equivariant homology groups of the stack of representations of this quiver, but now with coefficients in the sheaf of vanishing cycles for the potential. And so there's some correspondences that define an algebra structure. And similarly, one can build analogous representations. And this, again, was described, it was really in this case of the critical coha that was described in Jan's paper. I forget the title now, but you can look there for this kind of general.
So in the quiver with the potential case, the torus T, how does that?
It should preserve the potential. That's right.
And so acting on, because unlike in the Hilbert schema case, you have a base C2, so the T acting on C2. But in this case, you have a quiver with potential.
Yeah, and I didn't tell you what T is, right? But you'll recall from last lecture, we constructed quivers with potential from toric threefolds, describing certain categories of compactly supported coherent sheaves on toric threefolds. And there you have the subtorus of the toric structure torus, but you need to look at the subtorus that preserves the Calabi-Yau structure, which Jan was alluding to earlier in the talk. And the fact that it preserves the Calabi-Yau structure will imply that concretely in terms of the quiver, it will preserve the potential. And so then this sheaf of vanishing cycles will be equivariant with respect to that subtorus, and you can make sense of these kinds of groups.
Okay. Yes.
Maybe I don't know pedagogically whether it's a good place to say that this pre-projective coha is just a special case of this full coha.
Yeah, I'm going to say on the next slide. Yeah, yeah. At least in the C3 case. Yeah, I'll mention that. Okay. So now we want to generalize. And before trying to generalize to a kind of general toric threefold, let's just try to go from C2 to C3, following the kind of strategy that I've been building up towards here. So from this perspective, we're thinking maybe of the first objects that we should build are actions of these kind of cohomological Hall algebras and Yangians, and that maybe later we'll see that they in fact factor through the algebra of modes of some vertex algebras. So we're going to do a bit of a detour and talk more about cohomological Hall algebras. And at the end, I'll come back to the kind of relation to vertex algebras. And in the next lecture, we'll really spell out a lot of the somewhat conjectural details about that. Okay. So I'm now going to talk about the work on this topic by Rapcak-Soibelman-Yang-Zhao. And so to begin, I mean, this predates their work, but recall that we can similarly consider a stack of compactly supported coherent sheaves on C3 instead of C2. And just like last time, this can be identified as a stack of representations of a quiver that now has 3 loops instead of 2 loops, because C adjoin XYZ has 3 generators instead of 2 generators. And we would like all of these loops to commute, so we should have relations that enforce that they all commute. But there's a very cool observation that in this case, those 3 relations all follow from the critical locus equations of a single potential. And this is the sense in which quivers with potential naturally show up in describing coherent sheaves on threefolds. And we, of course, in the last lecture gave a much more kind of structural analysis of that type of phenomena, but this is sort of the simplest example. So in this setting, we have a quiver with potential, and as I was just saying, we can define the Kontsevich-Soibelman cohomological Hall algebra in this setting. I'll call that H of C3, so it's the cohomological Hall algebra of this quiver with potential. And it turns out that in this sort of simplest case, there's a kind of so-called dimensional reduction result, which various people have proved. I think maybe the original version of it was in one of the Kontsevich-Soibelman papers on this topic, but there are several other kind of statements along these lines by now. But it implies that in this case, the cohomological Hall algebra of C3 actually gets identified with the one that we would have built out of the kind of C2 Nakajima quiver using the pre-projective Koha construction. I guess in terms of matching up the algebra structures, as opposed to just the vector spaces, well, again, I think you guys described this in your paper. Maybe a more general statement appears in a paper of Yangian-Type that's called like on 2 Koha.
I think Ben Davison wrote an appendix to our paper with Jiren when he showed it in general that the multiplications agree. So
right, I was going to mention that as well. Yeah, exactly. I'm not so clear-headed on exactly what the distinction between that appendix and the results in Yapping and Goofing's paper is, but yeah, that I usually cite that as well. That's right. So we have this kind of dimensional reduction, and actually similarly, we can introduce a framing in this situation, which is precisely the analog of the framing that we had in the C2 case. So we can put 2 arrows here with a single vertex, C to the R. And then we can add to the potential a term that looks like IJ B3. And you can see here that if you take the critical locus equations, if you take the variation with respect to B3, you're going to find the ADHM relation. B1 and B2 commute to IJ. And indeed, it turns out that analogously, this kind of dimensional reduction result implies that if you look at the analogous critical cohomology groups or Borel-Moore homology groups of this this quiver with potential that I've drawn here, the framed quiver with potential, it will agree with the homology groups of the kind of Nakajima quiver, the ADHM quiver that we had before. And here I've introduced some kind of funny notation to denote this quiver. So here I called the original unframed quiver QC3 because it was associated with C3, but now I'm going to call the framed version Q sub, and then I'm going to denote it by an object inside of the derived category of C3, dbco, namely the structure sheaf of C2 shifted down in degree by 1. And the reason for that is that this is an example of the type of quivers that show up from the construction we were explaining last time in the very simplest example, if you pick an object in the derived category. So I'll say more about the things we explained last time in a minute. I'll kind of recall that, but I just wanted to justify the notation, but this is just a notation for this quiver. Similarly, the potential here, I just mean this should now be called W sub O C2 shifted by 1. Okay, so far so good. But now, having made this kind of conceptual leap to rephrase the previous story in terms of quivers with potential in this kind of three-dimensional setting, there's right, so I kind of maybe implied this but didn't say it in words. Let me say first, so I said that these vector spaces are identified, but in fact, the actual representations are indeed identified as representations of these algebras, which are also isomorphic. But then the thing I wanted to say that's good about having generalized to this three-dimensional setting, so far I just said, oh, well, everything's the same, so you might say, who cares? But in the C3 case, there are more choices of framing, kind of many more interesting natural geometric framings, which correspond to choosing more interesting objects in the derived category of C3 than just the structure sheaf of C2. And the simplest example that you might consider to generalize just the structure sheaf of C2 is you might pick a more general toric divisor in C3. So, for example, if we take our object M to be the structure sheaf of each of the coordinate divisors, then there's a natural quiver that extends the one that we have here, which is kind of a three-pronged generalization of the ADHM construction. Yes. And it just looks like you add two additional framing vertices corresponding to the sort of two additional summands here. So this is like CR1, CR2, CR3.
These are they are additional parameters because your M does not depend on this Ri, on the multiplicities.
That's right. It's an extra choice you fix, which it's basically the choice of framing vector. That's right. And then similarly, you modify the potential with some other terms, depending on these other vectors analogously. And what is shown in Rapcak-Soibelman-Yang-Zhao, unfortunately, I didn't have enough room in the end to write sort of theorem, but this is maybe what I'll end up stating as one of their main results. So first of all, you can check that analogously to the previous case, if you analyze the homology groups, which are expected to form a module over hopefully some vertex algebra, or certainly over the cohomological Hall algebra by the statements that I was, the general statements I was alluding to above, this vector space again decomposes as a tensor product of Fock modules for Heisenberg algebras. But now there's this interesting point that the kind of formal level of each of the factors should depend on which of the coordinate planes inside of C3 each of these copies of C2 is wrapping. And moreover, the main theorem is that rather than just getting some representation of a tensor product of Heisenberg algebras, one finds a representation of some bigger vertex algebra inside of endomorphisms, or a representation sort of on this vector space, which does look like a tensor product of Fock modules. And this vertex algebra is defined as an intersection of kernels of screening operators, exactly analogous to the setting when we just had a single C2 inside of C3, where this was the Fagan-Frankel presentation of the W-algebra. But this gives a kind of natural three-parameter generalization of the principal affine W-algebras, where the three parameters, if you pick two to be 0, then one of them should correspond like to the rank of the GLR in the original story. And a similar family of vertex algebras was studied previously by Rapcak, but I think it's important to point out that there actually does not exist a proof that this family of vertex algebras, which was proved to show up in this setting, defined as an intersection of kernel of screening operators, there's not a proof that this vertex algebra is isomorphic, or this family of vertex algebras is isomorphic to the family of vertex algebras defined by Rapcak, or by Rapcak.
Yeah, because the
That's still open.
definition is not geometric, but there is sort of an idea how to approach that question. You should use an operation of the conformal extension of vertex algebras and the result of Prochaska and Rapcak, I guess, or maybe Prochaska himself.
So let me
When
comment.
you glue more complicated, it's sort of topological vertex procedure. When you glue more,
that topological vertex procedure is what shows up if you have divisors that have compact curve classes. And that's precisely the level of generality that we're trying to aim for in kind of our work. And in my shortly forthcoming paper about vertex algebras, I discussed some things along these lines. In this C3 case, I mean, as in the usual topological vertex, there's not really like any gluing to do.
Yeah.
But
you say that even here, is it really so? Because I think they described, maybe you're right, I think they described, of course, the basis, kind of, there is an explicit basis in this vertex algebra at the corner, and it's given by some 3D partition, but that the vertex algebra exactly the same, the vertex, the structure of the vertex algebra the same, yeah, maybe it's indeed somehow missing, yeah, maybe. And I have also a question. I forgot, you have stated a result that for compactly supported, for the stack of compactly supported sheaves, then it's the same as a stack of representations of this quiver with a potential. What about the framed? Did you state that something like that, that if you add...
Yeah, I did. And I did state that last time, and I'll restate it in a couple slides. I mean, much more briefly than I explained last time. But I do want to point out to kind of, maybe it's funny to say it this way, but to kind of continue listing things that weren't quite established in this original paper of Rapcak-Soibelman-Yang-Zhao. This quiver, which I should have mentioned was originally proposed by Nekrasov, although there was some kind of allusion to the fact that it looked like it should be describing something like sheaves supported along the union of the divisors, there was not actually a proof of that kind of statement. And our results do give like a kind of, if you like, an algebrogeometric interpretation of this kind of Nekrasov moduli space of spiked instantons, which this quiver was
actually
supposed to describe.
maybe, okay, so you know, it's an interactive talk. Yeah, Nekrasov, you see, Nekrasov did not give the answer in algebra geometric terms, as actually Atiya Ward and ADHM. So the instantons are not algebra geometric objects by their origin. You should know what are the real numbers. The actual ADHM equation, they involve Hermitian conjugate matrices. Okay, and similarly for Nekrasov, of course, he generalized the story and he used the generalized ADHM equations which involved Hermitian conjugate. It's a separate work, actually, even for ordinary instantons. It's a separate work at the time by by Donaldson and then Nakajima. When they completely restated, they kind of get rid of Hermitian structure. It's, you know, it's analogous to the Donaldson result that you solve some
it's like this idea that you can forget the real moment map
it's
equation
even like
if you're willing to
Narasimhan
quotient by
that
the
unitary representation, like irreducible unitary representations of the fundamental group of a curve, it's same as holomorphic stable bundles, and so higher dimensional generalizations to Donaldson and other people. Yeah, so, but when you have only one side, when you have this Nekrasov equations, it's not obvious. And so then what's your answer, or will you state it later?
right? Yeah,
What
well,
kind of
I sort of
shifts these are?
Yeah, so I sort of explained this last time, but I mean, I didn't specifically address this example, but it's part of this general notion of perverse coherent extensions. But in this case, the statement would be, it's a moduli space of objects in an abelian category, which is generated, it's in this kind of, in some perverse coherent heart of DB-Co, generated by these.
Yeah, I understand. Yeah, okay, yeah. Nekrasov will not be happy with this answer because it's sort of too abstract. Yeah, I don't know.
That's fair.
No. I mean, it doesn't mean that he would be right, being not happy. Yeah, but anyway, there are some other possibilities, but maybe we'll discuss it later after you finish your talk or your lecture course. Yeah.
Yeah, let's. We should. So one more thing about these vertex algebras I wanted to point out is, so Rapcak gave a different definition, which had a more representation theoretic flavor, but which was not manifestly symmetric under exchanging the three coordinate axes. So remember, we observed earlier that exchanging two of the coordinate axes in the C2 case induced the Fagan-Frankel automorphism or isomorphism between two different W-algebras. So in this case, when you give a screening operator presentation, that was basically the proof of the Fagan-Frankel isomorphism. The screening operator presentation can more obviously be symmetric under exchanging the parameters. But the explicit geometric description, analogous to defining the W algebra as a DS reduction, it's sort of, from that perspective, very non-obvious that you have this isomorphism like Fagan-Frankel. And in this sort of three-pronged generalization, the isomorphisms between the different vertex algebras that Guyotto-Rapcak would assign, which naively look very different, they have a kind of different representation theoretic origins, those isomorphisms were proved, and it was like a difficult proof, which in fact didn't use the screening operator technology, interestingly. But people like Linshaw and Kreutzig, I think maybe it's them too, maybe there's one other co-author, have some papers about this, and they prove these things, but they're really like non-trivial results in vertex algebras. So from that, by kind of conservation of hardness, it's clear that there really is some meaningful content to the statement that this screening operator presentation actually agrees with the Guyotto-Rapcak definitions. Okay, so now let's move on to the generalization. Okay, so I'm going to quickly recall the things that I explained in the last lecture, and which I was kind of alluding to a moment ago. So if you fix a toric Calabi-Yau threefold, satisfying some hypotheses, and an object in the derived category, which you might think would be like the structure. So this could have been like C3 on the last page, and then the object would be something like the structure sheaf of C2 or of some more general divisor, shifted in cohomological degree. Then there's a theorem which we proved, but as I explained last time, parts of it are sort of well understood and uses many other people's work. So there exists a quiver, first of all, just depending on the threefold, such that the moduli stack of perverse coherent, compactly supported perverse coherent sheaves on the threefold is equivalent to that of finite dimensional representations of a quiver with potential. And moreover, when you fix this auxiliary object M, together with a little piece of extra information I'll mention in a minute called a framing structure, then there is a framed quiver with potential, which extends the kind of principal unframed quiver that you would get just from the threefold, and such that the stack of representations of the framed quiver with potential also admits a geometric description. So here, MF of YM denotes the stack of so-called F-framed perverse coherent extensions of M. And these are, I'll recall, a moduli space of iterated extensions of the object M with itself, as well as the compactly supported perverse coherent sheaves on Y, together with an isomorphism of the underlying iterated extension of M with some fixed choice of iterated extension of M. And a typical example that would have been the example that you use in all the previous examples of a framing structure is just to take an isomorphism to require an isomorphism with the trivial extension of M. So then you're considering iterated extensions of M and these compactly supported guys, but such that M isn't actually extending itself in an interesting way. That's an example of the type of moduli spaces. And yeah, they depend on this choice of framing structure, which maybe I'll say a little bit about later. Definitely next lecture, I'll emphasize it a lot. As I was saying, this kind of space of choices of framing structure turns out to be somewhat conjecturally related to a kind of space of different modules that you can consider for the given vertex algebra. And you start to see some kind of more intricate aspects of the representation theory of the vertex algebras showing up, which is very cool and exciting, but probably I won't be able to explain in too much detail today. In any event, this is the statement of the kind of first theorem in my paper with Miroslav Rapcak, although again, following many other people, as I said. And this is what we described last time. And an example of this type of framed quiver is exactly like the things we were describing on the previous page in the C3 case. Now, following the results of Yan that I was mentioning earlier, if we fix the stability condition for this framed quiver, we also prove, again, following the results in his paper, that there's a representation of the cohomological Hall algebra of this threefold, defined as the cohomological Hall algebra of this quiver with potential. There's a representation of it on this kind of categorified enumerative invariant, which is defined as the critical homology groups with respect to the sort of homology groups with coefficients in the sheaf of vanishing cycles of these the moduli spaces of stable representations with respect to the fixed stability condition of this framed quiver. So that's the sort of second main theorem, again, in the preprint, which is already out, joint with Miroslav Rapcak. And in fact, we also outline the fact that following some results of Rapcak-Soibelman-Yang-Zhao and in turn Schiffmann-Vasserot, we outline that, as I was explaining in the C2 case earlier, this representation of the cohomological Hall algebra constructed in this theorem actually extends to a representation of a sort of larger algebra, which has a triangular decomposition where the positive and negative halves look like the spherical cohomological Hall algebras of the threefold. But notably, where the kind of commutative Cartan part of the Yangian should depend on the choice of object here. And this dependence leads to so-called shifted quiver Yangians and so I should say these algebras, it's hard to call this a theorem because the algebras are sort of, and their representations are sort of defined just in physics, but if you kind of trust these physicists, which I do, then maybe this is almost a theorem. The statement is that this representation extends to this larger algebra, and this larger algebra can be identified with the so-called quiver-Yangian that was defined by Lee and Yamazaki. I'm sorry that their names didn't fit here, but they have a series of papers describing these kind of bigger affine Yangian-type quantum groups, and those appear to be exactly the ones that show up in this kind of setting when you try to extend these representations analogously to what I was explaining above. So this was the kind of main content of the first paper that we had. And now I want to say a bit following what I was explaining before, the sort of outline in the C3 case of how this should lead to vertex algebras from divisors on Calabi-Yau threefolds. So let's let Y be a toric Calabi-Yau threefold, satisfying the conditions we had before. And let's let S be a toric divisor on Y. Now we can decompose S. So first we can think about the underlying reduced subvariety of Y. So we can look at S reduced, this reduced subscheme, and it's going to have some decomposition into irreducible components. So I'm going to let this kind of curly D just denote this index set for the irreducible components of our divisor. Sort of in terms of the original divisor, they're like the reduced irreducible components. And then we can write the kind of class, you know, I'm thinking of this as a Cartier divisor, but we can think of the kind of class, the V divisor of S. It's going to be some sum of the classes of these irreducible components with multiplicities determined by some positive integers. And now the object that we'll be interested in considering in order to build this kind of framing is the kind of semi-simplification of the structure sheaf of S. Well, this shouldn't have the direct sums here, but that's okay. There's a small typo in this slide. Sorry, I prepared this in a bit of a rush. So we consider this object, this direct sum of these structure sheaves of the reduced irreducible components. These multiplicities should not be here.
You mean RD is absent, is just a direct sum of...
That's right. It's more, it should be called the semi-simplification of the structure sheaf of the underlying reduced subscheme. So let me call it like this.
Yeah, that's what, you know, it's a bit confuses me. I already asked you that question for a single C-square example, which you started with. You can assign this RD as some additional parameters, but here you included it in the divisor, and you can consider, I don't know, like you consider this as a fat divisor, like, for example, as we did with Emanuele and other people, like C-square with some multiplicity. And it's not obvious that when you do it one way, like with a non-reduced divisor is equivalent to what you get when you do this semi-simplification.
Yeah, so let me clarify. The notion of framing structure in our construction is supposed to capture that distinction. So the input data is you just fix the kind of the reduced thing, the reduced object. That's the so-called choice of M. So for example, in the simplest case, you take the structure sheaf of C2. That's your object, shift it down by 1. Now you consider the moduli space of all possible iterated extensions of the structure sheaf of C2 with itself and some structure sheaves of points.
And
But now in particular,
inside you have the structure sheaf of a fat divisor, and that's what you meant when you consider two different framings for the same quiver as we can. Okay.
exactly. So part of the data is you choose the requirement that you have an isomorphism of the underlying iterated extension with your favorite choice of underlying iterated extension, which you could choose to be either just the plain direct sum or this fuzzy divisor.
Yeah, but then you get two different
Different moduli.
coherent, yeah, but and therefore different representations, different vertex algebras. Yeah,
Exactly.
I remember that in the story with Emmanuel, we got the same W algebra of GLR, but different representation. That's exactly.
Yeah.
Yeah.
And that's the general expectation. There'll be sort of one vertex algebra, but the heuristic is if you take the completely decomposed thing where there's you have just trivial extensions, that should give you the full free field realization, as we saw in the simplest examples, like what Schiffmann-Vasserot proved. Whereas if you take, I'll say this in a minute, if you take the kind of fully extended framing structure, that corresponds to the vacuum module. And really, there's a kind of space of different framing structures in between that you could choose. And those should correspond to different sort of partial free field realizations. And this is the sense in which, as I kind of cryptically said at the end of the second lecture last time, you can see these kind of parabolic induction maps for W-algebras naturally coming from the geometry.
But
somehow,
these moduli spaces, they're not related by wall crossing, or they do?
I think of them more as gluing together into a sheaf. Like somehow, yeah, I said this kind of at the end last time, and I'll explain this next time.
Okay.
Let me just try to go through what I have today. And yeah, next time is about the sort of details of, you can see a lot of very nice aspects of the representation theory of W-algebras coming out of this geometric picture. And I'll explain in more detail next time, but I'll state the basic conjectures, like what I was saying in words a second ago at the end of the next slide, which is all I have left. So I guess if I finish in another 10 minutes, then it'll just be 2 hours just. So let's try to do that. Okay, but this was a typo here. So the initial object you pick should always be this kind of simple reduced thing. And then later in the choice of framing structure, you can put in which extension you want. Right, so let's consider this as our object. And then following the results of the previous page, this induces some framed quiver with potential. And there'll be some kind of categorified enumerative invariant, sort of like categorified Vafa-Witten invariant, defined by the critical cohomology groups of the stack of representations of this framed quiver with respect to some choice of stability condition. And you need to be a bit careful about which one you choose, but in any given example, it's usually clear what you want to choose. And again, by the previous slide, we should have a representation of an affine Yangian-type quantum group on this, this vector space. So this is our sort of input. And then the simplest way to state the conjecture is that this representation should factor through the algebra of modes of a particular vertex algebra, V of YS, which we give a definition of combinatorially analogous to the definition that I explained given in Rapcak-Soibelman-Yang-Zhao in the C3 case. We kind of extend that definition in a kind of, well, I'll say more about that next time. Let me not try to say too much, sorry. So we define these vertex algebras as the kernel of screening operators. And the conjecture is that this module should identify with a canonical free field representation that we use to define this vertex algebra. We define it as the intersection of some kernels of screening operators inside of a kind of free field lattice type vertex algebra. And here I've chosen just the trivial, here when I say F0, I chose the trivial framing structure, which corresponds to requiring that the underlying iterated extension of these structure sheaves of copies of S is just the direct sum, or structure sheaves of the reduced irreducible components of S is just the direct sum of those. So that object should correspond to the free field representation. But if you think about just the structure sheaf of the divisor itself, potentially thickened, right? If you have these multiplicities RD, that is also some iterated extension of these underlying guys, the sort of fully extended thing, the actual structure sheaf of the divisor. So that defines a framing structure as well, a kind of distinct canonical framing structure in this setting, which, for example, if you took the structure sheaf, if you took the divisor to be like the, rth order infinitesimally thickened C2 inside of C3, then the framing structure would be like requiring you have an isomorphism with that, and that would lead to this, principal nilpotent endomorphism on the framing vertex, as in the Chuang-Kreutzig-Diaconescu-Soibelman paper. And so generalizing their results, it's sort of natural to conjecture that if you pick this framing structure, you should find the actual vacuum module for this vertex algebra as the kind of geometric module for this different choice of framing structure. And more generally, there's some kind of other framing structures interpolating between those, which we expect to correspond to other modules. So now let me quickly, on this last slide, kind of explain a little bit more about what that kind of looks like. So
can I go back to, you mentioned about lattice
sorry.
with pi ys. And so
sorry, your mute is going on and off. You're now muted again. I can't.
Okay.
Can you start again?
Can you hear me now?
Yeah, perfect.
Good. So can you explain briefly say what is the lattice corresponding to the lattice VOA pi ys? Yes.
Right. So pi of
is
ys
that the homology, some kind of a homology of y?
So it's the following thing.
Mm-hmm.
Yeah, exactly. The homology of the components S. So we fixed this decomposition, right?
Mm-hmm.
So now pi of ys is going to be a tensor product, first over all of the different irreducible components, D in frac ds. And then for each of these, if you have like a single, reduced irreducible divisor, then you can take the lattice vertex algebra generated by H2 of SD with Z coefficients.
Okay.
And then tensor with just a Heisenberg algebra on H0. So this is kind of like a lattice extension of what Gronowski-Nakajima would find. And in fact, in the last chapter of Nakajima's, the very last chapter of Nakajima's book, he explains that it's also natural geometrically to find such lattice vertex algebras. And where do they come from? They come from the situation where you have a moduli space of sheaves that doesn't necessarily have a fixed first Chern class, but it allows the first Chern class to vary. And then the sum over the first Chern classes, which are valued in this H2, is what gives rise to the lattice extension. So the kind of modifications of the quiver representations that we build these out of correspond not only to Hecke modifications of the sheaves at points, but Hecke modifications of the sheaves along curve classes, which is the reason that you find this lattice extension.
Or that's the zero homology, and the other one is the second homology.
You get a lattice for H2, but then you just get a normal Heisenberg algebra on H0, and then you get a tensor product of these, as in the plain C2 case where there's no possible H2, you get a tensor product of this to the RD.
Okay, thank you very much.
So you get this big tensor product of kind of lattice vertex algebras corresponding to these reduced irreducible components. And then there's some natural way of introducing screening operators. And this is in the forthcoming preprint draft available upon request. It should be out in like a week. Probably it would be out this week if I weren't preparing slides for these lectures every day. But yeah, this construction is all kind of, thank you. Sorry, you have to leave. Okay, so finally, let me just get to the kind of end here. So we proved in terms of these abstract definitions that anytime you have a kind of factorization of the structure sheaf of your divisor into the structure sheaves of two other divisors, like you can write it as an extension, there's a natural embedding of vertex algebras that comes from forgetting a screening operator. And the natural conjecture generalizing the picture we had in the beginning with the relationship between the affine Yangian of GL1, its coproduct, and the free field realizations of principal W-algebras, is that there should be some coproducts on these shifted affine Yangians, which kind of they kind of extend the usual existence of these coproducts on shifted Yangians in the finite case, which should be compatible with these free field realizations in exactly the analogous sense. That's the sort of main conjecture that remains to be proved that I don't right now have a significant approach to. But in the case that Y is C3 and S is RC2, this structure just recovers the results of Schiffmann-Vasserot and Kreuzig-Diaconescu-Soibelman and gives a geometric interpretation of this coproduct and of these parabolic induction maps between principal affine W-algebras. And more generally, if you consider this family of singularities, these kind of XMN singularities defined by this equation, and resolutions thereof, let's call them YMN, then for any pair of partitions of M and N respectively, there's a natural divisor in YMN, and the conjecture is that the shifted Yangians, this should say, there are lots of typos here. I was getting desperate because I had to come to the lecture. The shifted Yangians that show up in the geometric setting should actually be those of GL little m little n hat. And moreover, the vertex algebras that show up here should be those of the W-algebras, not necessarily principal W-algebras, corresponding to the nilpotents determined by the choices of partitions. But these will be inside of GLM/n, where m is the total number of points in the partition, which isn't necessarily equal to little m. I'll explain more about this sort of richer set of conjectures later, but the big sort of punchline is that this gives a kind of geometric approach to proving an affine superanalog of these Brundtland-Kleshev isomorphisms between shifted Yangians and finite W-algebras, which exist in finite type A. And so there's this kind of amazing, still somewhat conjectural link between the representation theory of general type A affine W-algebras for arbitrary nilpotents, in fact, superalgebras, and the kind of geometry of coherent sheaves on all of the different divisors inside of these threefolds. And so I'll try to kind of flush out that correspondence, and you'll see that there's a lot of very convincing evidence, although this is still conjectural. As I say, there are many partial results verified, and in fact, this latter isomorphism, in the case where n is 0 in the non-super case, I do prove this in the forthcoming preprint. Okay, I better stop there. It's been a couple hours now. Thanks for listening.
Thank you very much. And this 3D analog of Hagen-Frenkel duality is what? Just symmetricity with respect to S3 invariance of the W-algebras with interchanging of epsilon i's, or what? Or
do you mean in the C3 case, the stuff I was talking
about
earlier?
There is, you know, this Katz moduli algebras, it's two-dimensional Calabi-Yau story. When you upgrade to shifted Yangians, probably they are No, actually, I'm not sure whether they're 3D objects, but so let me be unprecise. Is there an analog of this Fegen-Frenkel duality in 3 dimensions?
Yeah, so I would say the expectation is that because these vertex algebras all have sort of geometric constructions, which are manifestly invariants of the underlying geometric data, anytime you have a discrete automorphism of your threefold, if it maps one configuration, like a choice of threefold and divisor, to some other divisor, if you have some discrete automorphism that, I mean, it doesn't even need to be discrete, I guess. If you have an automorphism of your threefold that identifies two divisors, then you should expect that the corresponding vertex algebras are the same. And that should be the kind of generalization. And this really leads to
but the level for Fegen-Frenkel is not entirely geometric. It's kind of, it was a mixture. Yeah. It used the level is a shift of a minus dual Coxeter number by some equivariant. So it's kind of, I'm not sure.
I mean, in the absolutely most general case, it might not be true that this parameter has a name sort of to begin with, but
Yeah.
the expectation should be, if you have this automorphism of your toric threefold, it's going to induce some identification of the torus with itself, and then some automorphism, of the equivalent homology of a point. And that's kind of the analog of the level that you see showing up. But I'm sympathetic, like there isn't going to be some easy, obvious interpretation in terms of Lie theoretic data, like minus H check in the general story.
Yeah.
I mean,
Okay. More questions?
Yes. So on this page in the middle with the parabolic induction, and you have this W-algebra mapping to the tensor product. So how is the KRKT with the different levels for related
right.
to the original
Yeah,
level kappa?
question. So they are not the same. That's why they're denoted differently.
Yeah, that's why you're having different notations.
I think it's just going to be so. So it's a relatively easy exercise because the proof of this map is actually quite easy, and the calculation of the levels is just an exercise in remembering. Well, come on, it shouldn't be hard.
So
it just has to do with the fact that because we're changing the rank, the H check in all of these examples.
Dual constant number is also changing as well.
Exactly. Yeah. So it's more or less, I think in all of these cases, right? But that's true. It will be minus H check for the relevant rank, minus epsilon 1 over epsilon 2. And then you need to sort of, because H check is different, you get a different number. But let me just quickly comment.
I see. So in each case, the kappa is still the dual constant number in their corresponding GLR, and with minus 1 over epsilon 1 comes epsilon 2.
Yeah, 2 over
1.
Yeah.
Okay, I got it.
Yeah, and let me just say the proofs of these kinds of statements, and similarly like the general statement I have above here, it's not a deep thing. It's simply that we defined this as an intersection, I equals 1 to, r plus t minus 1 of the kernels of some screening operators. But this always embeds into an intersection of all of these kernels, except we forget one of them. So that let's say k not equal to r minus 1. And then what you notice is that the screening operators sort of only act, each of them only acts on this tensor product of Heisenberg algebras kind of pairwise. So if you forget the middle one, then you can kind of naturally factor the screening operators, and it's sort of obviously just the tensor product of intersections of the first r minus 1 many screening operators, and then the next t minus 1 screening operators. So it's really kind of a tautological thing once you have this Fagan-Frenkel isomorphism to observe the existence of this this embedding of vertex algebras here. And that's kind of the flavor of the proof of this this statement here.
Okay, I've got it. So also in the conjecture, you have this super version that with m and n. While m is in the even part, n is the odd part. But in the geometric setting for the ymn, is there a reason that m and n one is even or odd? you can see that
I would
definition
say
of x, which is it's just z to the m, w to the n.
it has to do with
how the resolution was.
yeah, if you look at the curves, like the exceptional curves in this resolution, and you look at the structure, so it'll be some chain of P1s, and there'll be some -1 curves, and there'll be some 0 -2 curves. And like some of the curves will be rigid, some not. And this will have the same structure as if you make a choice of simple roots in the superalgebra, not all choices are equivalent, unlike in the plane case, because you can choose different numbers of super roots versus normal roots. So for example, if you take the most standard decomposition, you usually think of GLM/n as some kind of square matrix like this. If you choose the usual simple roots, there'll be only a single one that is super, and all of the rest of them will be plane. And analogously, there is a resolution of this singularity for which you have all -2, 0 curves except one in the middle, which will be a -1 curve. And similarly, there are other resolutions which correspond to sort of different choices of simple roots in GLM/n. But that's the nature of the correspondence. It has to do with the rigidity of the exceptional curves that show up in this resolution.
Okay, thank you. Okay, so probably in the future, I'll email you lots of questions.
Great, yeah, I'll be happy to receive them.
Oh yeah, it's very
all right.
nice.
So I think we have the longest lecture given by Dylan today. And so his final lecture will be tomorrow at the same time. Thanks again. And
Thank
see
you.
you tomorrow.
Yeah, see you tomorrow.